In this video, we will look at a mathematical model for the flight of a glider, and to do this, we'll derive a set of differential equations and test that model in Kerbal Space Program. Hi, I'm Scott Vaughn, and I've been having a lot of fun using the game Kerbal Space Program to inspire learning in science and engineering, technology, and math. And if you'd like to see other lessons like this one, check out my website at sites.google.com, view KSP Math. Now the first thing we'll do is derive a set of equations that provide a simple model for the flight of a glider. That derivation uses the language of vectors and calculus, and so it could provide an introduction to those topics. We'll use the computer to solve the system of equations with different input parameters, and thus reveal the fascinating behavior of a real glider and the interplay between the lift, weight, and aerodynamic drag on the glider. We'll then compare our simple model with the more complex mathematical model built into the game Kerbal Space Program. So here's a glider in a standard coordinate system, and we've got a velocity vector indicated here. So that little arrow indicates that that's a velocity. It has a magnitude and a direction. And there's an angle theta here that is the direction of that velocity relative to the horizon. We could think of it as the pitch, but more precisely it's really just the direction of the velocity relative to the horizon. And our goal here will be deriving equations both for the speed, that's just a scalar number, v, as a function of time, and the direction, theta, which is also scalar, as a function of time. So we're solving for both of these quantities as functions of time, and we'll discover how the velocity will be going up and down as it is affected by the drag and the weight and the lift of the glider. So I have the standard unit vectors I and j indicated here, but I'm going to add into that additional unit vectors that are convenient to describe that motion and to derive equations for that motion. So the first thing to do there is to create a unit vector that I'll call t. That unit vector t is in the same direction as the velocity vector. And then I'll create a normal vector that is always perpendicular to the direction of travel. We'll call that n. Now that unit tangent vector is going to have components that are cosine of theta in the x component and sine of theta in the y component. We can see that because, first of all, this is a unit vector and the angle here is theta, and you could think of this as having this being a right triangle in the picture as it's drawn here, with an x component that is the cosine of theta and a y component that is the sine of theta. And as this angle theta increases or changes in this first quadrant, there's an equal angle theta right here. And just like the unit tangent vector is cos theta sine theta, this unit normal to the path of the glider, it's negative sine theta cosine theta. And we can see that because the angle theta that is between velocity and the horizontal will exactly match this angle theta between the unit normal and the vertical line, the vertical axis in this coordinate system. So the x component of my unit normal is actually negative of the sine of theta, this opposite over hypotenuse. Again, this is a length 1 vector, so the hypotenuse is 1. And so this is the sine of the angle theta, but has a negative because when the angle is positive, the unit normal will be here in the second quadrant. The y value for the unit normal will be the cosine of theta. It'll be this length here. So now we introduce the three forces that determine the motion of the glider. So first there's a drag force, force due to drag. That's parallel to the direction that we're traveling. There's the force of weight, and then there's the lift. So it's only these three forces that we're modeling, the weight, the drag, and the lift, and we have another vector here that is the velocity that's resulting from the interplay between the lift, drag, and weight. So now we create a mathematical model for how it is that those three forces affect the velocity and the pitch or direction of the velocity of the aircraft. So we'll say the sum of all the forces, no external force, no other external force, just these, The sum of all those forces is the mass of the glider times the acceleration of the glider as a vector. And we can write that acceleration, how it relates to the velocity, as it's the derivative of the velocity vector over time. Okay, then with m as the mass of the glider, let's write expressions for each of those three forces. And let's start with the force due to the lift. So force due to lift can be, from experiment, determined to be 1/2 times the density of the air times a coefficient of lift that we'll take to be a constant, the surface area of the glider, which we'll just also take to be a constant, times the scalar velocity, that is just the speed squared. So as obviously the speed increases, there's generating a larger amount of lift. We could also say that, as the density decreases, there's less lift. Changing these values can be affected by the way in which the glider is oriented according to the airflow, but we'll take all of this to be a constant in this derivation here. So basically, the thing that really changes is the speed, and as the speed changes, that determines the lift. Now, I think one thing that's kind of interesting to do here is just look really briefly at a dimensional analysis of this force due to the lift to see that it is in fact a force vector. So looking at the dimension of the units here, I would say the 1/2 is dimensionless. It's a dimensionless value. The density of the air I could express as kilograms per cubic meter. The coefficient of lift is something that would generally be dimensionless. And then you've got area of the glider, the surface area of the glider, which is primarily about the wings, but not only entirely the wings, but it's a constant area of the glider that we assume here, and it would have units that would be square meters. So this is meters squared. And then you've got the velocity, which here is just the scalar speed, which is meters per second, but it's squared. So let me just write that as meters squared per second squared. And then looking at these units here, we've got meters to the fourth divided by meters to the third. So that's just meters. So our units become kilogram times meter per second squared. And there is a mass times acceleration. So this is something that we could write as mass times acceleration. We could write as units of kilogram meter per second squared, or newtons. So the units of this expression check out as being in agreement with mass times acceleration generally, as we'll see all of them do. Now what I have right here is actually all a scalar, and I really want to create the vector that is the lift on the glider, and so I know that lift will be we'll model it as being exactly normal to the direction of the velocity. So in our simplified model, we'll just say the lift is exactly the total sum of the lifting force is normal to the velocity. And so this gives me the direction of the lift. It is this magnitude times this direction, and that direction is along the normal vector. So in the same way, we can look at the force due to the drag, and the drag is parallel to the velocity, but always opposite to the velocity, and actually also, just like experimental modeling of drag, it's found to be very similar to the mathematical model for lift, which is, I think, also really just fascinating. A formula to determine drag is 1/2 times the air density times a different coefficient, that would be the drag, which we'll here assume to be a constant, times the area of the glider. Now it's the same area, so but how that area determines the drag is based on that coefficient of drag, which is something that's also found experimentally, that we'll just take all of this to be a constant in this derivation. And then we have Also, that drag is proportional to the square of the velocity or the speed, and it's in the direction of the velocity or the unit tangent. So I'll put the unit tangent vector here, but I almost forgot the negative because the drag is exactly opposite to the unit tangent vector. So I'm including a negative right here to account for the fact that the drag is opposite to the direction in which we're traveling and the direction of the velocity. And so the next force to describe here is the force due to the weight, and the first thing we could do here is just say that it is down, and it's down with respect to this coordinate system, and I'll write that initially as mass times the acceleration due to gravity, so that's what g is, gravitational acceleration, which again I'll take to be constant near the surface of the planet. But I can write that here as, the weight is the mg. The negative j indicates that the weight is a vector downwards in our coordinate system. Now, we want to add all of these vectors together, all of these forces together, and I've already described this in terms of the normal and this in terms of the tangent vector, but this is in terms of the standard unit vector, j. So I want to find a way to rewrite this guy in a way that I can add conveniently with the normal and unit tangent, so that I can add all these together and equate it to this expression, and that's where I get the equations of motion from. So now how is it that I can express that unit vector j and this force due to the weight in terms of the unit normal and unit tangent vectors? So one way to do that is to write the force due to the weight projected onto the unit normal and the unit tangent vector. So what I'm talking about is a projection onto the unit normal vector of the force due to the weight. So this is something from the Calc 3 class, multivariable calculus, analyzing projections of one vector onto another that I wanted to illustrate this way. So a formula for that calculation uses the dot product. It's the force due to the weight dot the unit normal vector divided by magnitude of the unit normal vector times the unit normal vector divided by the magnitude of that unit normal. Of course, the magnitude of the unit normal is 1, so we have this as the force due to the weight. Let me make a comment that the force due to the weight, because it's negative mg times the unit vector j, I could say it's 0 in the horizontal component and negative mg in the vertical component. It's just negative mg times the 0, 1 vector, which gives me that. So in order to do the dot product, then I can look at the force due to the weight, which is this vector 0, negative mg, dotted with the unit normal. And that unit normal we have already established up here as negative sine theta cos theta. And this is all divided by 1 times the unit normal vector divided by 1. So this is still a vector that I'm constructing here. This is the magnitude of the vector and this is the direction. And what we're really talking about is the component of the weight that is normal to the path. So then what happens when you do that dot product? 0 times negative sine theta, that's 0, plus negative mg times cos theta. Of course, that's negative mg cos theta, and that represents the magnitude of the component of the weight normal to the path. The negative n represents the direction of that weight. So that's the component of the weight that is right here. Now there's also a perpendicular component to the weight that is tangent, and it's the sum of those two vectors together, the sum of these two vectors that make the total weight, the total force due to the weight. So we'll derive that component of the weight that is tangent to the path in exactly the same way, doing a dot product with the force due to the weight with the unit tangent divided by the magnitude of the unit tangent, which of course is 1. So here's the weight vector and the unit tangent vector, and doing that dot product, I have 0 times cos theta, which is 0, plus negative mg times sine theta, which is mg sine theta. I've got, therefore, negative mg sine theta as the magnitude and negative t as the direction. So it's opposite to the direction of travel. So it's a vector that would be sort of like this guy. It's the component of the weight that is in the direction of travel. It's basically what's making the glider fall backwards. The normal component and the tangential component make the total weight of the glider. And so I'm claiming that the total weight of the glider is the combination of those two forces, and you can see it sort of geometrically, but there's also kind of a nice little algebraic way to confirm this. This is the weight, the force due to the weight as I've just derived it, and I'm claiming that it's the same as this expression. This is the weight in terms of the standard unit vector j. So in other words, this unit vector j is really equivalent to the sum of these two unit vectors, normal and tangential components. So let's investigate whether cos theta times n plus sine theta times t actually comes out to be j. And so this is cosine times the unit normal vector, and this is sine times the unit tangent vector. And multiplying cosine in, you have cos times negative sine plus cosine squared. I'm just distributing this. Here I'm just distributing the sine function, so I have sine times cosine in the first component and sine squared in the second component. And of course, if you add these two vectors together, this is negative and this is positive. These are going to add to 0, and cosine squared plus sine squared is going to add to 1. So in fact, that is equivalent to the unit vector j. So now things are really starting to come together. We have the force due to lift in terms of the unit normal, the force due to drag in terms of the unit tangent vector, and the force due to weight expressed in terms of the unit normal and unit tangent. So now we can add them all together, and we'll equate that to the mass times acceleration. So then here we have the force due to lift, force due to drag, and force due to weight all written together, and we want to set that equal to the mass times the acceleration, or we'll write it this way to relate the velocity vector. So that is the sum of all the forces is the mass times the acceleration of the glider, written in terms of its change in velocity over time, the change in the velocity vector over time. So what we'll do next is just collect together these two terms, which are both in terms of the unit normal, and combine together those terms, which are in terms of the unit tangent. So we're really close, and what we need to do, what's left now, will be to derive the equations. We need an expression for this in terms of unit tangent and unit normal. So we'll need to get the derivative of this velocity vector over time. Now, in order to get an expression for the derivative of the velocity, what I'll do is I'll start with the velocity vector as being just, let's say, the magnitude of the velocity times the unit tangent vector. Rather than continuing to write it this way, I'm going to just say v without the little vector arrow indicator. So I mean v, here v, the v is actually the linear speed. It's just a scalar value representing the speed multiplied by the direction of the velocity given by this unit tangent vector. So the velocity vector is the speed times the direction. So this represents the magnitude of the velocity, the speed, and this is the direction of the velocity. So we're looking at the derivative of the velocity vector over time, and that's going to be found using the product rule. We've got a product of two values here, a scalar times a vector, but the product rule still applies. So we could do the derivative of the first factor over time. So that's the change in the speed over time. That's the linear acceleration times that unit tangent vector plus the speed, or the linear velocity, times the derivative of the unit tangent vector. So let's write that for the moment just like that. And we'll need to expand what exactly that is in terms of the unit normal. So we've got it written right up here that the unit tangent is this sine theta, cosine theta vector. But remember also that theta is some function of time. And so in taking a derivative of the unit tangent vector with respect to time, we actually need the chain rule. So recopying, I have dv dt times unit tangent plus v times the derivative of the unit tangent. Now the derivative of the unit tangent, what you could say here is taking a derivative of the unit tangent, you take a derivative of the first component, that's the derivative of cosine. The derivative of cosine is minus sine, but this is cosine of theta, and theta depends on time. So there's a chain rule factor that's going to produce a result that looks like this. You'll say the derivative of cosine is minus sine, and then the derivative of theta, which is d theta dt. In this case, we're taking a derivative with respect to time. So we get the derivative of cosine theta times the derivative of theta with respect to time. And then looking at the derivative of sine, the derivative of sine is cosine theta, but then the chain rule factor gives me d theta dt. So we have cosine theta times d theta dt. So it's the chain rule that's producing that extra factor. It's also worth noticing that the derivative of the unit tangent is actually the unit normal, and that all we've done is added in this extra factor of d theta dt because that angle theta depends on time as well. So now we'll have linear acceleration. So this is basically the component of the velocity is changing that's causing it to speed up or slow down along its tangential path, plus the component of acceleration that is causing it to turn. We can factor out that d theta dt and say it's the speed times d theta dt times this negative sine theta cos theta, which is the unit normal. So the acceleration vector is broken up into the component of acceleration that is in the direction you're traveling and the component of the acceleration that is causing it to turn. And now we can equate that to the sum of all the forces acting on the glider. So now we've put it together that the sum of all these three forces, lift, drag, and weight, relate to the velocity in this way. And here's the force due to lift, drag, and weight in terms of unit normal and unit tangent. And we've taken the components that are normal and gathered them together, and the components of those forces that are tangential, and we've combined them together. And now we've got an expression for the actual change in the velocity over time in terms of the unit tangent and unit normal as well. That's what we just completed just previously, and now that's fit in there. So what happens at this point is we can equate the normal components on each side of the equation and the tangential components on each side of this equation. And so the way that'll work is like this. We'll just multiply in this factor of the mass of the glider, distribute, and rewrite it. So multiplying mass times velocity d theta dt, I wrote that first to match this the unit normal component over here, and multiplying this mass times the linear acceleration here, and just wrote it second because it's going to match that guy. So now we'll say this normal component of the forces equal this normal component of the total sum of all the forces, and the tangential component of the sum of all the forces is the tangential component of the mass times acceleration, or total force, on the right side of the equation. I mean, the other thing to say here is that these are two vectors that have to equal, and therefore their components have to equal. And that's what we're doing here. So there's the first equation. I'm just removing the vector notation here because I'm just equating these scalar values on each side of the equation. And then the second equation that must be true is this one. And there we've derived two equations a system of differential equations that model the interaction between the lift and the drag and the weight of the glider and how it relates to the velocity and the angle theta, which is the direction of the velocity relative to the horizontal. So now this is a system of differential equations that we can actually solve. We'll use the computer to solve it here, and then we can check to see how well that model corresponds to what we can see in Kerbal Space Program. So we're solving this system of nonlinear differential equations for the speed and direction of the glider. And I refer to it as nonlinear because one of the things we're solving for is this speed, this velocity squared, which is really just speed as a function of time, the magnitude of the velocity, that's squared. And so that's why it's a nonlinear differential equation. Both of them are nonlinear differential equations. Okay, and how about a quick recap of what all of these variables are? Well, it's these two variables, v and theta, that we're actually solving for. V referred to as the velocity, but technically actually the speed. It's the linear speed of the glider in the direction in which it's traveling, and then theta is the direction that it's traveling relative to the horizon. We can think of theta as the pitch, but technically it's really the direction of the velocity. So the craft could be pitched in any particular direction and be going up or down, and it's really the direction of its motion that we're really tracking with the variable theta, the direction of the velocity. Not technically the pitch, but in a very simple model here, we can just sort of assume that it is pointed exactly in the direction it's traveling and refer to the direction of travel as the pitch and the direction of the velocity. Okay, so these are the actual variables that we're solving for. And all these things that are listed underneath are also variable in a sense. We can put different numbers in for these, but they are constant in the system of equations. They are parameters of the system that we would fix to be a particular value that would produce a particular solution depending on what each of those are, right? So m is the mass of the glider, the rho is the air density, CD is the coefficient of drag, and CL is the coefficient of lift, A is the surface area of the glider, and G is the acceleration due to gravity. All of these are things that I'll keep constant in the solution to the system. Okay, for just one more step of rewriting this system of equations before we put in the computer to solve it, I'm going to divide both sides of both equations by the mass of the glider, by m, because that's a constant, and it'll be just convenient. So we'll divide both sides by m for both of these. And if we call that equation 1 will become, after you divide out the m, you'll have v d theta dt equals, well, let's write it as rho coefficient lift area over, and let's say 2m, because the 2's in the denominator, times the mass, and then that'll be v squared. And now if we're dividing out the m, we'll just get negative g cos theta here. And then equation 2, this one, when I divide the mass of the glider on both sides, then we'll just have dv dt on the left side of the equation. We'll have negative 1 over 2, and I'm dividing by m, so I'll just say this is negative rho, coefficient drag, area of the glider, divided by 2 times the mass, velocity squared, minus, and again I divided the m on both sides, so this will be just g sine theta. So when it comes to typing in this system of equations into the computer, I'm going to take this as a constant, that as a constant. I'm going to assume, therefore, that the air density is constant, the coefficient of lift is constant, the area of the surface area of the glider is constant, and the mass is constant during the flight. So this will be a combination of constants that I'll just call mu for lift, and this is a combination of constants that I'll just call mu for drag, and of course it has a negative as part of that system of equations. So this is what we'll put into the computer when it comes to solving the system. So before we actually type this into the computer, we can actually make some interesting observations about some particular solutions by just stepping back one step and looking at this way in which it was expressed. Okay, for a first example, suppose that the coefficient of lift was 0. So basically I've removed the wings and pointed straight down so that the initial angle here is -90. So if it's pointed straight down and it doesn't have any wings anymore, basically this guy's going to go to 0, and the cosine of -90, that's going to go to 0. So this whole thing wipes out, becomes 0 under this condition. Now that means the d theta dt times the velocity will equal 0. Of course, the velocity will increase, but the angle won't change. There'll be no change in the angle. It'll be continually pointing down. And so what will happen is we can actually look at the change in the speed. It's basically what we'll uncover here is the terminal velocity, an expression for the terminal velocity. So by taking that assumption that the coefficient of lift is 0 and it's pointed directly downward, we could conclude there's no change in the angle. The change in the angle over time has to be 0, and that means it'll just continue going down. No surprise, no lift, and it's pointed downwards. But the velocity will increase, and we can actually figure out what that. At least we could determine when the velocity no longer changes, and that is when the acceleration is 0, which would be it's reached its terminal velocity. So we can find that particular value by just solving this equation right here. Well, I've already made the assumption that theta is -90, so I can plug that in here, and the sine of -90 would be -1. So we arrive at an equation that looks like this. Let's solve for the velocity. So there I've just multiplied both sides by a negative. I've flipped this coefficient over on the other side and multiplied by g, and now there's two solutions algebraically, but I'm really just finding terminal speed. The speed at which its drag has stopped it from accelerating, and it's just going to continue to fall at that speed unless it's already hit the ground. So we'll just find the positive solution, and this is the terminal velocity. Knowing the weight and the air density, the coefficient of drag, and the area of the surface of this object, I could compute the terminal velocity. Okay, and then another particular solution that we could find is if somehow magically the drag were to disappear. We could just remove this and set it at level flight. So let's take a look at that. Well, if coefficient of drag is 0 and the angle is 0, so then that factor goes to 0 and the sine of 0 is 0, and so this whole term zeroes out, and that means there's no change in the speed. It would just continue to move at a constant speed. If there wasn't any drag and it was level, then we wouldn't slow down because there isn't any drag to slow it down, and now we could figure out when this is 0, which is basically we could find the speed at which it would just remain level if it didn't have any drag and it was already level. So with no drag and level flight, what's the speed that would just keep it at level flight? And let's assume that it's already moving. So I mean, assuming that the velocity is not 0. And I want to figure out what's the speed that would just keep it at level flight. That's called the trim velocity. Well, if the angle is 0, the cosine of 0 is 1, so that just gives me an equation that looks like this. Air density, coefficient lift, area divided by 2 times the mass, v squared, minus g times the cosine of 0, 1, equal to 0. And let's solve for what that velocity would be. I'm setting v to be not 0, so that the only way this equation could be 0 is when d theta dt is 0. So move g over on the other side, and like before, just flip this fraction that's in front of the v squared. And there are two solutions algebraically, but we're just talking speed here in one direction or the other, so let's just take the positive solution algebraically. This is the trim velocity. And I think it's kind of interesting that that is just like the terminal velocity, but involves the coefficient of lift. It's kind of the speed at which, if there was no drag, that it would just stay at level flight. Of course, if you add in drag, that'll slow it down and it'll fall. I'm just momentarily there comparing trim velocity and terminal velocity, the expressions are identical except for this coefficient. So those might be some interesting things to experiment with and compute in particular examples. Okay, so let's return now to this set of differential equations that we're going to solve and use the computer to solve it. It's complicated to solve and definitely need the computer to help out here. In this case, we will look at some input parameters. So I'll refer to this mu L as a lift constant. It's not really the coefficient of lift. It's a lift constant that derives from several other constants, as I've discussed. And mu D, this is the drag constant. We're going to need an initial speed and an initial direction. And of course, we're solving for V and theta as a function of time. We'll also include an initial position. We'll just make the initial position 0, 0 so that we can track how high it goes and how far it goes, and we can actually plot its path through the air. Now the whole thing is taking place with only an x and y component, so it's really something that's happening in a two-dimensional plane. We don't have any crosswinds or any change in lift and drag from one side to the other. All of those things are real-life complications that are excluded in this particular simplified mathematical model, but this will give us a result that's very interesting and interesting to compare with real-life examples. And in particular, we'll look at a more complicated mathematical model for the flight of a glider in Kerbal Space Program and compare this result, or the results that we get here, with the results in Kerbal. So this is Wolfram Programming Lab and the Wolfram Mathematica language that I'm using. And the first example that I have here will model the Gull, which is one of the stock airplanes in Kerbal Space Program. And you can see that I have initially identified 2174 meters as the initial height. Initial speed, I'm going to use 159 meters per second. The initial angle, 0. My mu lift is 0.011 and mu drag 0.0001. And the gravitational acceleration I'll take to be 9.8. So here's where I ask the computer to solve that system of differential equations. I'm using V for the velocity that I'm solving for, and theta, the variable theta for that angle. So I've written in here just exactly the same as that set of differential equations that I had derived. V prime equals negative g times sine theta minus the mu drag times the velocity squared, and the function v that I'm solving for times theta prime equal to negative g cos theta plus mu lift times the velocity squared. And I have here set my initial speed to be v0, which I've defined up here, and my initial angle to be theta 0, which I've defined up there. I'm solving for these two functions, v of t and theta of t, on an interval from t equals 0 to 120 seconds. I take the solutions from this numerical differential equation solver routine that's built into this language, and I input those solutions into these functions that I define here, speed and angle, as a function of time. Now, once I've got the functions that are speed and angle over time, I want to figure out the position so I can graph the position. So I created another set of differential equations just for position based on the speed and the angle of the velocity. Let me explain a little bit where that comes from. So what I'm talking about, as soon as I've used the computer to solve for speed and direction for the velocity and the v and the theta, I can use that result, given those solutions for the speed and the direction of travel from the previous system, I can immediately find the position x and y in the two-dimensional plane using the fact that the dv dt is a combination of the dx dt and the dy dt, the change in the horizontal position and the change in the vertical position over time. And they relate to the velocity and the direction, let's say the speed and direction over time, by these differential equations. And so I'm solving another set of differential equations for the function x and y as a function of time. With the initial condition, we can just arbitrarily decide where we start the time at some point 0, 0 in the two-dimensional system, and we could just track the position x and y over time with whatever initial conditions we had for the initial altitude and the initial speed and the initial angle. And so we'll get ultimately solutions for the position x and y over time. So we can plot that as well and look at the behavior of the glider under the action of all of these forces with different given initial conditions. So then with those initial conditions, what does the computer find as a solution? We can plot the speed and angle over time and see that it begins at about 160 meters per second. That was the initial speed, drops off pretty quickly down to around 20 meters per second, jumps back up to roughly 130 and begins to oscillate around 100 meters per second. This is the angle plotted over time in degrees, reaching up maybe to 45 or 50 degrees, dropping down to maybe negative 50 degrees. So the pitch is oscillating over time, up and down, as it gradually regains horizontal flight. So what's happening is, as it's falling, it's picking up speed, which generates enough lift for the airplane to recover and go back up again. And as it starts to go up again, it loses that lift. It slows down and loses that lift, which means it will finally begin to fall again. But then when it begins to fall, it picks up speed, gains lift, comes back up again. So it'll do that under the right conditions. It'll oscillate like that up and down, which is pretty fascinating. So this is a plot of the x position and y position solutions over time, and we can look at how closely this is to actually what happens in the game. And this is actually a plot of the y position. I'm just looking at what the height is over time. I mean, actually, really what was happening is, of course, in real life, it's a matter of experimenting to figure out what are the correct coefficients of lift and drag. And so I was looking for a coefficient of lift and a lift constant and a drag constant that would match closely to a particular set of data that I had collected. In first example here, that's what I'll do. So we can look at a particular flight and see that it matches very closely. We'll see that it initially was at the 2174, that was my initial height, and it reaches up to, well, just over 3,000 meters. Looks like it hits about 3,100 initially, and then it drops back down. So let's take a look at an example flight. Okay, so here we are at the Kerbal Space Center on the runway with the Gull, and I'm looking at my altitude up here at the top of the screen, setting it actually to be the radar altitude to the ground level, so I can confirm that it's about 1 or 2 meters right here on the ground. Preparing for flight here, we can track the speed right here at the bottom of the screen in the nav ball. And one of the things that I'm going to do is this SAS is the stability assist system, and it's going to keep it at level flight or directly on our prograde direction. So it's like it assists the flight controls. But what I want to do is, so obviously we're under powered flight here, generating thrust. You can see the thrust right there that is generating lift and bringing the airplane up into the air. But at some point, what I want to do is quickly shut off the engine so that it's gliding, and then also turn off the SAS so that I can just let the aerodynamics of the airplane cause it to oscillate up and down. So I'm just waiting to gain enough altitude and speed to give this a try. So I'm shooting for an altitude of about 2,000 meters and around 150 meters per second. So here I'm just leveling off. You can see that it's oriented the pitch is nearly 0, and I'm on the prograde vector, so I'm pointed in the direction that we're traveling. So here I have the option to hit the shutdown engine to turn off the thrust quickly, and as soon as I hit the shutdown engine, I'll hit the SAS button to turn that off to watch it oscillate from the aerodynamics of the lift and the drag and the weight. So approaching engine shutdown right there. So then as soon as the engine is shut down and the SAS is disabled, the plane pitches up and the altitude increases, and we reach up to about 50 degrees pitch, and the altitude increases to 3,000 meters. After that, the plane loses lift and slows, the speed drops, and the pitch drops down to about negative 50 degrees, and the altitude drops down to about 2,300 meters, at which point the plane is beginning to gain speed again and increasing lift, and the oscillation begins to repeat. Now I thought I would try that again, this time to create a loop-to-loop. So this time starting at about 1310 meters in altitude, but going faster at 205 meters per second. But what I'm really doing is sort of testing out to see whether the same constant lift, constant and drag constant will still predict the behavior with just different altitudes and different speeds. And in fact, it did. So that was something satisfying to see work out. So with that altitude and that speed and the same lift constant and drag constant, I've got the speed dropping off to maybe around, could be around 40 and then picking up again. What I'm seeing here is the angle goes past 360 degrees and then begins to oscillate. So in the way that it's solving the system here, it just, once it passed 360, it just uses an angle greater than 360 as you go above and below 360. So it loops around once. We can see that in this plot of the position one loop, and then it begins to oscillate up and down after that. And so we can sort of see what this mathematical model would have predicted for the altitude. It looks like it's predicting pretty close to 2,800 meters from the initial height of 1310. So let's see what happens. All right, so I'm initially flying downward here to use gravity to help pick up speed, get past 200 meters per second. And then I'm getting ready to hit engine shutdown and level off. Engine shutdown right there, and then it pitches up, and it was at 1310, and now the altitude is gaining, the pitch is increasing. Looking for it to reach about 2,800 meters and flip over. And it just about does. Doesn't quite flip over and doesn't quite reach that 2,800 meters, but pretty close. And now as it's falling, it's picking up speed again. And the lift is going to bring it back. It's going to recover and level off again. So I think that's all pretty good work for Jeb, the test pilot. And thank you, Jeb. Let's return this plane. Okay, Jeb, what do you say? Before you go, we try one more. Awesome. All right, let's do it. So I went looking on the Kerbal X website for a craft file that might demonstrate this loop-the-loop behavior that I discovered in the solutions to the system of differential equations, and I found one, the WG1 by Christian Hakem. Thank you very much, Christian, for posting this craft. It worked really well. Now, I've spent a lot of time learning about the aerodynamics of flight working on this video, and it's all been fascinating. All the while I've been hoping to determine, using information given about a particular craft in the game, how to determine appropriate lift and drag constants for my mathematical model. While I do have some ideas how this might work, it got really complicated. Rocket science is easy compared to the aerodynamics of flight. So instead, I'll just say that, first of all, finding the coefficients of lift and drag are experimental anyway in real life, and that's what I ended up doing again. And they aren't really constant either. And all of this is a fascinating topic, but this video is long enough already. So maybe sometime I can come back to this topic in a future video, looking again more closely at the aerodynamics in the stock game, or perhaps adding even more realism with the Ferrum Aerospace Research mod. So after some experimentation, I found constants for the mathematical model that would accurately model the behavior of this WG1 glider. So back here in Wolfram Programming Lab, I have a model for the WG1 glider, and in the clip that's playing right now, I'm going to shut down the engine and disable the stability assist system at an altitude of about 2483 meters with a speed of about 203 meters per second. Pretty nearly level flight, and this is the lift and drag constants that I found that pretty well model the flight of this glider. So again, goes through solving the system just as before, and the results are produced here. We'll see the speed drop very quickly down to around 50 meters per second, pick up again close to 150 meters per second, and begin to oscillate around 100 meters per second. This completes a loop, so it passes 360 degrees and then begins to oscillate above and below that 360 degree angle. And here's a plot of the position in the two-dimensional plane of its altitude and horizontal position. So it does a loop, and then it almost does another one and begins to oscillate up and down relative to its initial height being about 2,500 meters. So again, just producing a list of the altitudes just so I can sort of check how well does the mathematical model compare with the actual data in the game. We're starting at about 2483 meters, and I'll look for it to reach up around maybe 3870 meters in altitude before falling down to about 2,500 meters, about its initial height. We can see that here, just right around its initial height before climbing again. Now, the lift to drag ratio that's implied by these constants that I found here are not that different from the stock Gull sailplane that I'd already modeled and flown in KSP before. And this really surprised me. I know the WG1 glider has better lift and less drag than the Gull, and I think the explanation mostly comes down to the fact that the values for lift and drag coefficients simply aren't constant. They aren't constant in real life, and they aren't constant in KSP. In particular, these values change with speed and orientation, as we can clearly see in the game. We only assume those values to be constant in order to derive a relatively simple mathematical model to demonstrate this kind of behavior that we see in real life with paper airplanes and real gliders and in KSP. In other words, we can use similar constant parameters for both planes in the mathematical model to demonstrate their flight, but the WG1 glider generates more lift at the right orientation, which allows it to complete a loop, while the Gull didn't. So let's check how close the mathematical model fits to the actual data, that is, to the results in the game. Waiting for engine cutoff and disabling SAS. I had initial height at 2483 meters, initial speed about 203 meters. The model predicts max height to be about 3870 meters as it completes a loop, and predicts the glider will return to about 2,500 meters after that first loop, and we expect the speed to oscillate around 100 meters per second. The model also predicts the second peak in altitude after the loop to be about 3,300 meters, and this is confirmed. And all of these values check out. Of course, I find a drag and lift constant that does fit these values, but it's still amazing that it's only these two values, along with the initial height and speed and the system of differential equations, that all together will model and thus really predict all the other values that followed. So, to conclude, I hope you found this topic as interesting, educational, and as fun as I have. Before this project, I understood there are 4 fundamental forces that govern the flight of an airplane, and that a plane must generate thrust to overcome drag, and that thrust, combined with the surface of the plane, can generate lift, which allows the plane to overcome gravity. I hadn't thought much about what happens when you remove the thrust. I expected the plane to go into a dive and head straight down, but I see now, under the right conditions, even as a plane goes into a dive, its wings can generate enough lift to recover from the dive, and it might oscillate between diving and recovering and diving as the lift, drag, and gravity determine the speed and direction of travel, even without thrust. I've seen that behavior in the path of a paper airplane, and now I've derived mathematically how it can occur and demonstrated it in Kerbal Space Program. So I'll wrap up by returning to the solution to the system of differential equations and to this publicly available applet at the Wolfram Demonstrations project. You can find this applet by just typing gliders in at the website shown here. The code in this applet is much more sophisticated than what I created in my demos earlier. This app provides sliders for the speed and the angle of release and for the drag. And to simplify the numbers, the system being solved is essentially the same as the one that I had derived earlier. We could just rewrite the system that I derived earlier in this form by redefining the gravitational acceleration constant g set equal to 1, and then you just set the value that I had determined was a trim velocity, make that equal to 1. The trim velocity that we established before, make that equal to 1. And as a result, you'll end up with this value d that is the ratio of the drag to the lift coefficients. And it just simplifies the form of the system of equations. And now, with this equivalent set of differential equations to what we were solving before, it's pretty neat to now have this interactive that we can sort of play around with and sort of discover some special solutions that are kind of interesting to think about. For example, that idea of the trim velocity. Now, if I have that equal to 1, what does that look like? Let's set that initial velocity equal to 1. And let's make the initial release angle 0. So it's just flying level, and remove the drag so that there's 0 drag. So we get this perfectly horizontal line. And what this is illustrating is that if there's no drag to slow this glider down, if it's released with a velocity that is sufficient to generate lift that exactly cancels out gravity, that's why it'll just fly straight on perfectly level from then on, because it's got an initial velocity that is just enough to generate lift to just cancel gravity, and there's no drag slowing it down, so it just continues on perfectly horizontal. Now, this would never happen on a planet with an atmosphere. You need an atmosphere to generate lift, but then when you have an atmosphere, that also produces drag. So, of course, you can imagine flying, for example, on the moon with no atmosphere and thus no drag, but then you would have no lift, and in order to stay maintaining flight, you'd have to get enough speed just to stay in orbit. So, of course, all of these are interesting questions that you could experiment with flying gliders and airplanes on different planets in Kerbal Space Program. If I ever get around to doing another video on this topic, that might be something to play around with. Here's another particularly interesting solution. We see it released downwards at an angle of -π/3, or about -60 degrees, with a velocity equal 1, which means the trim velocity, it's exactly at trim velocity. So the lift generated by the glider exactly would cancel gravity at that speed. But because it's released downwards, gravity is adding speed, which gives it more lift, which brings it back up, and it's going to go faster now than trim velocity. And without any drag, it heads upwards until it loses lift, and gravity brings it back down. And with no drag, this just repeats over and over and over again. Certainly not a realistic solution, but kind of fun to experiment with and discover. So I think I'll wrap it up here. We've derived equations for the model of the flight of a glider. We've looked at lots of different solutions under different conditions, both by graphing the solutions and looking at how well they are modeled, or how well they model flight in KSP. So that's enough for now. Thank you very much for watching.